First, I would like to thank the organizers for giving me this opportunity to present my work in this very nice conference. So the title of my talk will be Superconductivity Beyond Standard Models. But first, acknowledge my collaborators on the topics that I'm going to discuss today. So Vanildo, who was my former PhD student, now he's a postdoc at the University of Minnesota. Catherine Pepin from CA Saclay. Rafael Caetano, who is my student from UFG. Thomas and Xavier. Okay, so my talk will be divided in two parts. So in the first part of my talk, I'll be talking about a two-loop RG calculation of a model applied to the cuprates, and I'll explain the role of SU2 pseudospin symmetry. And in the second part of my talk, I will use the same framework to discuss a model to describe iron chalcogenides. Specifically, I will focus on the iron-selenide compound. Okay, so I'll start here with the ubiquitous evidence of a charge order phase in the cuprates. So I will start here with the NMR experiments where we found a field-induced charge order phase. This is a long-range order, static order, inside the superconducting dome. And this was very interesting because it really established the existence of this phase. Later on, there was some resonant X-ray experiments where they managed to find a CDW signal above TC. And this is short-range correlations. You can see here that the line is different from T star. I'm going to talk about this later. After that, there was also some SEM and X-ray scattering where they managed to determine the symmetry of the charge order phase, and it's a D-wave symmetry order parameter. So it's similar in this respect to the D-wave superconducting order parameter. And the modulation of this charge order phase is given by the wave vectors that connect the tips of the Fermi arcs. And these are the so-called hotspots. So I'll come to that in a moment. So I'll just briefly mention here, everybody knows this phase diagram, the cuprates. So here there's the ferromagnetic mod insulating phase. As you dope the system enters in this very mysterious phase which sets a T star. And this T star potentially crosses the superconducting dome and ends up at a quantum critical point at T equals to 0. Of course, there's also this strange metal phase and a very high doping. One recovers from a liquid regime. Okay, so the standard model to describe cuprates is, of course, a 2D Hubbard model. So I'll just show here the Hamiltonian of this model. So you have the kinetic term plus the local interaction term here given by U. And so the main question in this field is, of course, if this model contains enough physics to describe high TC. And if yes, so what is the heating order responsible for the pseudogap phase? So many candidates enter in the arena. So there are proposals for pair density wave, phase, loop current order, fractionalized liquid, SU2 pseudospin symmetry, so on and so forth. And a model to describe the cuprates, you can, of course, decouple the Hubbard U using Hubbard-Stratonovich transformation and derive a low-energy effective theory involving both bosonic STW order parameter and fermionic excitations near the hotspot. So this is the so-called Spin-fermion model. And, well, it's a well-known result that this model has a D-wave superconducting phase due to the fact that the spin excitations is the pairing glue that leads to the pairing, the Cooper pairing of the electrons. But the same glue also leads to a D-wave charge order state. And this is related to the so-called SU2 pseudospin symmetry, which was originally obtained first by Metlitsky and Subisashdev in 2010. Later on, there was this very important proposal by Catherine and Efetov in 2013 that the pseudo gap, maybe due to the fact that at high temperatures the system cannot decide between charge order phase and superconducting order. So the SU2 pseudo gap composite order would be described by a matrix with both charge order and D-wave components. And this, of course, leads to many interesting predictions that will be discussed in the next talks by Demalia and Corentin. Okay, a complementary microscopic approach to address this problem is this so-called fermionic hotspot model, which is a Hubble-like model. And it's a purely fermionic analog of Abanov-Shubukov spin-fermion model. And includes all relevant interactions between the hotspot fermions. So we are going to use an RG approach to attack this problem. And the most singular behavior occurs at the hotspot. So the hotspots are these points here, the special points, which are the intersection of the underlying Fermi surface with the antiferromagnetic zone boundary. And we will linearize around these points, and we write down the partition function for this model. Also, we have to parameterize the interactions among all the hotspots. So we do this. We have many couplings here. And to relate this effective model to the 2D Hubbard model, we must impose that initially the couplings are proportional to the local interaction U. So even though this is this holds initially, you're going to see that as one renormalize the model, these couplings will flow to different values. And of course, we have to impose also a ultraviolet cutoff, and this is standard. Okay, this might sound a bit technical, but it is not. Actually, it's physical. So I'm just showing here some reasons why one should go at least to two-loop order in the RG scheme. So a two-loop RG calculation, or beyond, is necessary to include the self-energy feedback into the RG flow equations. And actually, the first non-analytic contribution to the self-energy arises at two-loop level. That means that at one loop, Z is equal to 1. So we have to go to two-loop to derive the RG flow equation for the Z factor. Okay, so we do this. So here are the diagrams that we have to calculate. So at one loop, we have the Hartree-Fock term. This diagram has no energy dependence. And at two-loop, one gets this sunset diagram, which is the first non-analytic contribution. And this diagram, we normalize the Fermi surface, the quasi-particle weight, the Green's function, spectral weight, so on and so forth. And we do this by renormalizing the couplings, the fermionic field, and also the Fermi velocities. So using a standard condition for the Green's function, we get this RG flow equation for the Z factor. We also have to calculate the diagrams related to the vertex corrections in this theory. And we get many coupled RG flow equations for the couplings. So I won't go much into detail about that. So we solve this theory. And by solving it, we get many non-trivial fixed points. In this two-loop RG approach, remarkably, only a single one is stable in all directions in the infrared limit. And this is the so-called hotspot point, or SU2 fixed point, is this one here. And one very interesting aspect of this fixed point is, even though initially the model is not invariant under SU2 pseudospin symmetry, the fixed point is. So what that means is the interactions that break the SU2 symmetry, the SU2 pseudospin symmetry, are actually irrelevant in the RG sense. This is what we mean by emergent SU2 pseudospin symmetry. Okay, so we can calculate many things. So this is the RG flow for the particle weight. So the Z flows to 0. That means that there are no coherent low-lying quasi-particle excitations at the hotspot. And that means that we get the breakdown of liquid behavior. We can also use the two-loop RG scheme to calculate the renormalized Green's function, the spectral function, so on and so forth. Okay, so a very important message that I want to convey here is that when we calculate the response function of this model, we get several responses which are actually related by this SU2 pseudospin symmetry. What it means is, so for instance, this charged order phase which exists in this model gets a SU2 partner given by this pair density wave phase. So what is a pair density wave phase? The pair density is a superconducting order parameter, but with a finite Cooper pair center of mass momentum. And this is a bit formal, so I won't go much into detail about that. But this pair density wave phase should be visible in the cuprates. And I'll flash here an experimental evidence that this is indeed the case. So the group of Seamus Davis published this paper in 2016, where they managed to map out the Cooper pair density. Here are the data. And by Fourier transforming this, they managed to show that the modulation of the Cooper pair density is given by the wave vectors exactly associated with the hotspots. So this is a bidirectional pair density wave. So, so this confirms, in a sense, a prediction of the so-called SU2 pseudospin symmetric theory. But what if we apply the same RG framework, meaning the two-loop RG calculation, to a completely different system? For instance, the iron selenide compound. So this is based on this recent work that I did with my student, Rafael Caetano. So why do we choose the iron selenide? And the reason is that this material stands out as having as the iron-based superconductor that has the simplest structure, one of the simplest structures among the iron-based superconductors. And actually, a monolayer on strontium titanate produces the highest TC among the iron-based superconductors. And this, of course, hints at a unconventional mechanism at work in this material. And from ARPES and also quantum oscillation experiments, they obtained the electronic structure of this material. And what they observe is that this material is described by many pockets, both around the gamma point and also around the zone, the edges, the brilliant zone. And these pockets has a rich orbital structure. So here I show dxy, dxz, and dyz. And this is the phase diagram of the material. So this is temperature versus pressure. So at zero pressure here, this pneumatic phase onsets at around 90 Kelvin here. And as we decrease the temperature, the system superconducts around 8 Kelvin. And there is no magnetic order here at zero pressure. But as we increase the pressure, the magnetic order appears, and the superconducting phase gets dramatically increased. So there is some interplay between this magnetic phase and also the superconducting phase. So we are going to analyze that using the RG scheme. So here I also show a very interesting recent result by Sproul et al., published last year, where they obtained the superconducting phase in the iron selenide is actually orbital selective. So what that means is they were able to extract from this data here the quasi-particle weights, for instance, of the normal state, and they got these numbers here. So you see, for instance, that the quasi-particle weight associated with dxy orbital is much strongly renormalized than the others. So dyz, for instance, is almost not renormalized at all. And this revealed a very unusual and unconventional form of superconductivity, which was previously unknown. And of course, this is related to the fact that this material is actually described by this new concept of Hund's metallicity, which means that it's an unconventional state which is halfway between a conventional metal and a multi-insulator. And this is actually a signature of Hund's metallicity, to have this very anisotropically renormalized quasi-particle weights in the system. So what we are going to do is to use a model to calculate things. So this is a very simple model to try to understand the properties of this material. So this model was originally proposed by Shubukov, Kodas, and Fernandez in 2016, where they calculated using a one-loop. Actually, they use a Parquet approach, but this is equivalent to the one-loop RG calculation. And what we are going to do now is to calculate using the same model, but using a two-loop RG scheme. So this is the parameterization that we use. And these couplings must be, of course, related on a microscopic level to both the Hubbard U and also the Hund's coupling. So the next step, we move on to calculate the linear response theory. So we can calculate many order parameters in this model. So here I just show you some relevant ones. So this is a SCW order parameter with a modulation described by Qx, and this is SCW with a modulation described by Qy. This is singlet superconductivity, and this UCS stands for uniform charge susceptibility. So we can also symmetrize and anti-symmetrize these objects to obtain a superconducting order parameter with S++ symmetry, with S+-, S+-, also the Pomeranchuk instability, so on and so forth. So what we are going to do right now is to derive flow equations for all these quantities in order to see what is the relevant one in the model. We need to calculate the Feynman diagrams. So this is the self-energy up to two loop. And we also have to calculate the vertex corrections up to two loops. So these are schematically the Feynman diagrams that we have to calculate. And once we do that, we obtain flow equations up to two loop RG order for the couplings, which are given here. And we solve these equations. So this is the plot here. Even though we start with very weak interactions in the beginning, these couplings, they shoot up. And they flow to a strong coupling regime as the energy scale flows to zero. So as you can see here, many couplings, they flow to different values depending on the orbital content of the pockets. And yeah, of course, this is, of course, very interesting. And this is the two-loop RG flow for the quasi-particle weight. So we managed to calculate also the renormalization of the Z factor here. And as you can see here, I just show you ZYZ and ZXZ. And as you can see here, they have different flows. So one is much more strongly suppressed than the other. And this is, of course, is the signature of this orbitally selective renormalization of the quasi-particle weight that takes place in this model. And the next step is to see what is the feedback of this renormalization of the Z factor in the susceptibilities of the system. So we do that. So here I show you the RG flows for the other parameter susceptibilities, both at one loop, at two loop, in order to compare. So at one loop, you see that the dominant instability is given by both S and D wave Pomeranchuk instability. Here, the the black line is the stripe type antiferromagnetic stability, which loses to the Pomeranchuk one. This red line here is S plus minus superconductivity, which is the fourth instability in the model. But as we include higher order fluctuations and also the two-loop self-energy effect, the flow of the susceptibilities change dramatically. And as you can see here, the leading instability becomes stripe type antiferromagnetism. And this is, of course, very important. And what that means is, at least in this model, the origin of pneumaticity is antiferromagnetism and not Pomeranchuk instability. So, but this is, of course, a calculation. And I'll come to my conclusions here. So for the cuprates, I showed you the hotspot model, and its emergent SU2 pseudospin symmetry captures qualitatively many aspects of the cuprates. And based on this theory, for instance, a novel bidirectional pair density wave slash charge density wave composite order was predicted, which was subsequently confirmed by STM experiments. And for the iron selenide, I showed you that an orbitally selective renormalization of the quasi-particle weight is obtained within an effective model for this material within this two-loop RG scheme. And this two-loop RG theory may provide a framework from an itinerant picture in which the role of orbital selectivity to describe the physical properties of some iron chalcogenide superconductor is taken into account. So with that, I thank you very much for your attention.